Hello, this is my video lab report for Lab 6, Magnetic Molasses. The purpose of this lab was to observe the motion of a magnet falling through a conductive tube and explain that motion using Faraday's law and Lenz's law. I also developed a computational model of the system and compared the simulated fall time to my experimental results. Experimentally, the magnet fell significantly slower than it would in freefall, taking about 1.24 seconds to pass through the tube. The simulation predicted a longer time of about 1.79 seconds. While the model successfully captured the slowing effect, it slightly overestimated the magnetic break. This lab is based on a few main physical principles. First, Faraday's law states that a changing magnetic flux induces an electromotive force. As the magnet falls, the magnetic field through each ring of the tube changes over time, which induces currents. Second, Lenz's law tells us that the induced current will oppose the change in magnetic flux. In this case, that results in a magnetic force that opposes the motion of the falling magnet. Finally, the magnetic dipole field equation is used to model the magnet, and this allows us to calculate the magnetic field at any point in space, which is necessary for determining the induced currents and forces in the computational model. In the experiment, we used a roll of aluminum foil as a conductive tube and dropped a bar magnet vertically through it while recording the motion on video. The entry and exit times were measured to determine how long the magnet spent inside the tube. For the purpose of analysis, the system consists of the falling magnet and the induced currents in the aluminum tube, while the surroundings include gravity from the Earth and small effects like air resistance, which were mostly neglected. From the video, the magnet clearly fell much slower than it would normally, with an average fall time of about 1.24 seconds. Instead of accelerating like an object in freefall, the motion seemed smooth and closer to a constant speed. This behavior occurs because the changing magnetic field induces currents in the tube, which create an upward magnetic force, and as a result, the net force on the magnet is reduced and the system approaches a near terminal velocity. To model this system, I treated the magnet as a magnetic dipole and represented the tube as a stack of conducting rings. Each ring experiences a changing magnetic flux, which induces a current using Faraday's law. That current then produces a magnetic force on the magnet. The model follows several steps: computing the magnetic field from the dipole, calculating the rate of change of flux, using that to determine current, summing the forces from all rings, and then updating the magnet's motion using Newton's second law. Here are the key functions used in the model. The dipole magnetic field function calculates the magnetic field at a given position relative to the magnet, and the flux function calculates how quickly the magnetic flux through each ring changes as the magnet moves, which is essential for determining the induced current. This slide shows the main simulation loop. At each time step, the code calculates the gravitational force and the magnetic forces from all the rings, and then combines them to find the net force. Using Newton's second law, the magnet's velocity and position are updated over time, allowing the simulation to model the full motion through the tube. The simulation shows that the magnet quickly slows down after entering the tube and then moves at a nearly constant velocity for part of the motion. The colored areas indicate the direction of the induced currents, with red and blue representing opposite directions. Comparing results, the experimental fall time was about 1.24 seconds, while the simulation predicted about 1.79 seconds. This shows that the model captures the overall behavior, but overestimates the strength of the magnetic braking. Overall, the results demonstrate that a changing magnetic flux induces currents in the tube, and those currents create a force that opposes the motion of the magnet. This leads to reduced acceleration and a near terminal velocity. The difference between the model and experiment can be explained by several factors, including an overestimated magnetic dipole moment, idealized assumptions about the conducting rings, and imperfections in the aluminum foil. The key idea is that the magnet's motion induces currents, and those currents feed back to oppose the motion, slowing the magnet down. Now onto the what-if questions. If the resistivity of the conductor were reduced close to zero, the induced currents would become much larger, producing a stronger opposing force and causing the magnet to fall much more slowly. Meanwhile, if holes or slots were cut into the tube, the current loops would be disrupted, significantly reducing the induced currents, and this would weaken the opposing force, and the magnet would fall closer to free fall. Thank you for watching.